Hello, my wonderful students and chemistry lovers. Today I'm going to talk to you about giant ionic structures. My name is Dr. Lotano Kwesili, and I'm going to serve as your guide today in this interesting lecture and conversation. Okay, so when we talk about giant ionic structures, it is important for us to state that ions within an ionic compound are like sodium chloride are arranged in neat and regular fashion, all right, known as a giant ionic structure, or what we otherwise call giant lattice structure. If you pay attention to the diagram to my left, you will see how the small positive sodium ion are being held together by electrostatic attractive forces and bound to their larger chloride ions, as it were. And this is what you have within the giant lattice or in the giant ionic structures. You find that different ions or oppositely charged ions are held together by strong electrostatic attractive forces, and they are bound together. However, because we are talking about giant ionic structures, the term giant here tells us that we're not just talking about a few number of ions. However, we're talking about large number of ions, in which case we are talking about millions, if not billions of ions that are held together by strong attractive forces. However, they are held together at regular and neatly placed fashion, where you have those oppositely charged ions alternating among themselves in a regular fashion within what we call the giant lattice or the giant ionic structure. The second diagram labeled B, gives us a better picture of what is happening. All right. What we are talking about is that here you have a typical crystal lattice of sodium chloride, where, of course, the small dots represent the sodium ion and the bigger knots representing the bigger negatively charged chloride ion is shown there using the small circle as you see. So the dots represent the sodium ion and the small circle represent the chloride ion. And if you pay attention to it, you will see that they repeat themselves at different regular patterns within the ionic crystals. Crystalline solids are known to have their particles being packed and arranged in regular fashion, and that is what we call crystals. I believe it's clear. Now, it is important to know that if you understand giant ionic structures, it's now easy for us to describe the key properties of different ionic compounds. There are 5 key points that we're going to use to describe the giant ionic structures. And in describing those aspects of giant ionic structures, we will do justice to picking out the key properties of ionic compound, which happens to be the ending part of our discussions in ionic compound. So pay attention to understand the 5 key points that describe the giant ionic structures, because again, we're going to use that to describe the key properties of ionic compound. And that will be the end of our discussion on ionic compound. Then we'll move to the next topic. Okay, so the first point here, or the first key takeaway, is that we have to understand that electrostatic attractive forces is the strongest kind of forces that there are when we start talking about chemical bonding. And because in giant ionic structures, we are talking about broad number or large number of oppositely charged ions that are held firmly within the lattice structure, you understand that it has high energy content. This is because, one, electrostatic attractive force is the stronger kind of force there is, now existing among millions, if not billions, of oppositely charged ions, which means these forces hold those numerous broad number of ions in place within the giant lattice or giant ionic structure. Therefore, you will agree with me that a great deal of energy is required if we are going to break up those electrostatic attractive forces or ionic bonds between those numerous number of ions. So because the electrostatic attractive forces exist again between millions, if not billions, of oppositely charged ions. You have them firmly held in place with the ions only vibrating in those lattice points where you find them within the crystal lattice. When we get to special topics in inorganic chemistry, in crystallography, I'm going to pay attention to describing how crystal structures are formed and describing how ions and particles are packed within the different crystal systems. When we get to that, we're going to dedicate a lot of videos in describing crystallography, formation of crystals, and description of different crystal structures that there are in chemistry. I believe it's making sense. So again, because of the strong electrostatic attractive forces between numerous number of ions within this lattice structure or crystal lattice as it were, you will agree with me that we will need to supply a great deal of energy if we must overpower and overcome those strong electrostatic attractive forces. This is key because in certain instances, we will need to break up those electrostatic forces to free up ions to move, because that helps us to describe another property of ionic compound or giant ionic structures, which is electrical conductivity. We are coming to that. Okay, because we need to supply a great deal of energy to overcome the electrostatic attractive forces or ionic bond holding this numerous number of ions in place within the crystal structure. You will agree with me that ionic compound or giant ionic structures will require great deal of energy or temperature to break. Hence, we can say that the first property of an ionic compound or giant ionic structures is that they have high melting point, and of course, they have high boiling point. Again, remember from Coulomb's law that it is not just the understanding of this lattice structure that helps us understand the strength of ion-to-ion interaction. It's also important we understood in our previous videos that the higher the magnitude of the charges in a given ionic compound, the stronger the electrostatic attractive forces, the stronger the ionic bond, and the higher the melting point and boiling point. And that is seen when you compare magnesium oxide against sodium chloride. Magnesium oxide has two ions, the magnesium 2 plus ion and the oxide 2 minus ion, having higher magnitude of charges as against sodium ion and chloride ion, which they have the magnitude of their charges to be 1. And this is reflected again in their different melting and boiling points. Because magnesium oxide has higher magnitude of charges, which is 2 in their 2 ions, you discover that, of course, they have high melting and high boiling points. So where you have magnesium oxide having 2,852 degrees Celsius as its melting point and having 3,600 degrees Celsius as its boiling point, you have sodium chloride that has 1 plus sodium ion and 1 minus chloride ion. Here you have lesser magnitude of charge, 1, 1. And that now reflects in that sodium chloride has a lower melting point and, of course, lower boiling point than what we have in magnesium oxide. Okay, so you discover that that sodium chloride now has a melting point of 801 degrees Celsius and has a melting point of 801 degrees Celsius, and of course has the boiling point of 1465 degrees Celsius. So what did we pick here? Ionic compounds, again, have high melting points and high boiling points. However, some ionic compounds have more or higher boiling points and higher melting point than others. And this is because of other factors, which I told you is that they are the higher the magnitude of the charge on a given ionic compound, the higher the lattice energy, the higher the stronger the ionic bond, the higher the ion-to-ion interaction, of course. By consequence, the higher their melting points when placed side by side with other ionic compounds with lower magnitude of their charges. And that is what was expressed to us when we discussed Coulomb's law and lattice energy being the expression of Coulomb's law. Now, that said, let's move to the second point. Now, if you pay attention again to this crystal lattice, what you discover again, because of the strong electrostatic attractive forces holding these ions in place, these ions are firmly held, they can only vibrate, but they are not mobile, they are not free to move. And when ions are flowing or moving, they carry electric current. Just like when electrons is moving or flowing or in motion, they conduct electricity. So because you have solid crystal or solid ionic compounds, within it, you have their ions held firmly within the crystal. They can only vibrate, they don't move about. They don't conduct electricity in solid forms. So the second property of ionic compounds is that in solid form, in their solid crystal, they do not conduct electricity. However, if by chance we're able to break up those electrostatic forces holding those numerous ions in place, we can free up those ions to begin to move within the system or within the solution, as it were. So if we subject a typical crystal lattice of sodium chloride to ridiculously high temperature, what happens is that the high temperature overpowers the electrostatic attractive forces acting between all of these ions, and those ions melt, or the sodium chloride melts, and once it's in molten form, the sodium ion is liberated and free to move, the chloride ion are free to move. And when ions are flowing or moving, they carry and conduct electricity. So the second property of ionic compounds is that in molten forms, they conduct what? Electricity. I believe it's clear. Now, the third point is here is that, of course, when a crystal of an ionic compound is placed in water, it dissolves, okay? And in dissolution, those ions that comprise the ionic compounds are liberated and free to move within the sodium chloride solution as it is. And of course, again, when ions are freely moving in solution, that solution is said to be electrically conductive because the motion of those ions carries with it the conduction of electric current. I believe it's clear. But we need to also remind ourselves of the chemistry in the dissolution of ionic compounds. It is important for us to understand that when you place salt or sodium chloride or table salt inside a glass of water and stir, what happens is that water molecules will aggregate or cluster around the surface, okay, or the outside of the ionic crystal of that salt compound. But what happens again is that you need to know that water molecule has a dipole moment. What we mean by that is that water molecules are polar, in that towards one end of it, the oxygen end, it has a partial negative charge, and this is because of the presence of excess lone pairs of electrons. Towards the other end of the water molecule, we have two hydrogen atoms which are said to be partially positively charged. If that is clear, placing salt in water and stirring makes water molecules to aggregate around sodium chloride, which is found in the surface or outside the crystal system of that ionic compound. And what now happens is that the negative end of the water molecule dipole, which is the oxygen end, they attach themselves, the oxygen end attach themselves, aggregate themselves around the sodium ion, because the sodium ion is positively charged and the oxygen ends of the water molecule dipole is negatively charged. So they aggregate around the sodium ion. The same way, in the same vein, you have the chloride ion, you have the water molecules aggregating or clustering around the chloride ion using their partial positive hydrogen ends. And when this happens, you discover that the water molecule begins to now exert a lot of energy and force, which ultimately pulls the ions apart and pulls them into the solution. That is the chemistry behind dissolution of ionic compound. I believe it's clear. And a certain kind of force of attraction is made when the sodium ion and chloride ion are yanked apart, that is breaking the ionic bond. A new kind of bond is made that aids dissolution of this compound. And that new kind of bond is called ion dipole forces or ion dipole attractive forces, which is a kind of intermolecular force. As a matter of fact, the ion dipole forces is the strongest kind of what we call intermolecular force. After discussion on covalent bonds, we're going to dedicate a series of videos just describing the different kinds of intermolecular forces that we have in chemistry. And we're going to use those description of those intermolecular forces to ultimately describe the property of different molecules that we have in chemistry. I believe it's clear. So you will agree with me that an ion dipole forces are made, or ion dipole attraction forces, attractive forces, are made when you have a neutral molecule that has a dipole moment, okay, clustering around different charged ions in a solution. What you make is called an ion dipole forces. So again, because water molecule has a dipole moment, you say that water molecules are polar. Water being a universal solvent, you can now describe it as a polar solvent. As a matter of fact, the third property of ionic compounds is that they can only dissolve in polar solvents like water molecules that have a dipole moment. And this is because they're able to make the ion dipole attractive forces that overcomes the ionic bond that holds the constituent ions in place within that ionic compound. I believe it's clear. Again, since ionic compound only dissolve in polar solvent like water molecules, it's also important for us to state that they do not dissolve in non-polar solvents or organic solvents. You're talking about solvent like propanone or acetone, okay, or talk of N-hexane, diethyl ether, chloroform, and all of those ionic, those organic compounds, okay? I believe it's clear. The fourth point here is that giant ionic structures, of course, can be quite hard solids. However, they are very brittle. They are brittle in the sense that they can easily be shattered into pieces, even though they are strong and hard, as it were, because of the strong electrostatic attractive forces. However, if we want to understand the fourth point, we will look at again the typical crystal lattice. Because you discover in the crystal lattice that ions of opposite charge are separated using those lines. At no point will you find ions of the same charge, clustered or arranged closely packed or close enough to the other ion of the same charge. However, if we apply a little stress on this crystal lattice by way of pinching the salt or hitting it, if some kind of mechanical stress is applied to this particular ionic crystal, what happens? There is a possibility of a distortion of the layers of these crystals. So much so that some of the chloride ions can come very close to other chloride ions, and some of the sodium ions can come closer to some of the sodium ions. And that creates a great deal of repulsion because like charges repel themselves. So if by any reason we're able to subject this crystal structure to some form of distortive forces, mechanical forces, we are likely going to shift the layers of these crystals, and accidentally like charges are going to come together and they're going to be a great repulsive forces. That is the chemistry that underlines and underscores the brittleness of ionic compounds, even though they are hard structures, as it were. I believe it's clear. This is very, very interesting. The fifth point here is that when molten sodium chloride conducts electricity, because we told you that molten ionic compounds conduct electricity. So when molten sodium chloride conducts electricity, of course, it splits into the two component elements that made the ionic compound in the first place. We're talking about sodium chloride metal, sodium metal, and of course, chlorine gas. These are the products of what we call electrolysis. As a matter of fact, because you have sodium chloride being broken into the component element, that's a chemical change. However, in electrolysis, what actually moves in the solution is ions and not electrons. As we go over to describing intermolecular forces and doing justice to the topic of chemical bonding, we're going to pay attention to describing what we call electrolysis when we get to the topic of electrochemistry. We're going to pay attention to this subtopic of electrolysis and describe them and simplify it for our chemistry lovers to appreciate, understand, and assimilate to better their chemistry. Okay, so again, this is a chemical reaction or a chemical change because we are using electricity to break up sodium chloride now into the elemental compositions, which is sodium metal and chlorine gas. Okay. And again, electrolysis involves the movement of ions in the molten compound, not electrons. However, if you bring a copper metal wire, which is known to be very conductive, that's what we use in wiring our house because of high electrical conductivity. If you bring the copper wire, what happens is that in the matrix and on the surface of the copper metal wire, you have what you call delocalized electrons. Electrons are freely moving, a sea of electrons. And that is why you have that metal being very conductive. So electricity is conducted when electrons are moving, as you have in the copper wire. However, in the case of the copper wire, it's just electrons moving within the matrix and on the surface of the metal. So that electricity that is being conducted does not affect the chemical property of that copper wire. So in that case, you discover that that is an electrical property, the movement of electrons within the copper wire to conduct electricity is a physical property. It doesn't involve a chemical change. However, as you can see here, in electrolysis, you have ions moving, okay, in the molten compounds. And of course, motion of ions ultimately produce what we call electricity, even though in this case, electrons are not moving. However, this particular instance, you have your sodium chloride changed into the elements that comprise it at the initial. So this is a chemical change. While the motion of electrons to conduct electricity in the copper wire is a physical property. It doesn't involve chemical changes, as it were. I said that to help us understand that when electrons are moving in a system, they carry electric current. And again, when ions is moving, maybe in a molten solution or compound, you again have them carrying electrical charges and conducting electricity. So again, the 5 key properties of ionic compound is that number 1, they have high melting point and high boiling point. Number 2, we also highlighted that when they are in dissolved or molten states, they conduct electricity. The third point is that they are brittle. So even though they are hard solids, when you subject them to some mechanical stress, you get those ions distorted and you're going to have great repulsive forces acting on them. And finally, we were able to talk about that ionic compounds can conduct electricity. And this happens in a process known as electrolysis, which we are going to pay attention to after we are done with describing the different other kinds of chemical bonding. We are talking about the covalent bonding, which is the next topic we are moving into. We are talking about after that the metallic bonding and intermolecular forces. Then we're going to take it from there and keep giving our chemistry lovers interesting topics that will help them upscale and better their chemistry. I believe you learned something in this lecture. I believe you saw how we used the typical crystal lattice to describe the different properties of ionic compound. With this, we have come to the end of our topic in ionic bonding. I believe you learned something. If this video made sense to you, if it added value to you, please kindly subscribe to my YouTube channel, which is Chem Class with Dr. Luther. And I also invite your friends to be part of what we are doing here for our chemistry lovers in Chem Class with Dr. Luther here on Facebook. Kindly follow our page, Chem Class with Dr. Luther. Share our videos so that you can get to those students that need some of the information we are dishing out. Subscribe to my YouTube channel. All our previous videos are now uploaded for your delight on our YouTube channel. The same handle is Chem Class with Dr. Luther on the YouTube channel. I believe you learned something. If you learned something, encourage me by sharing this video. Make your comment and like and share. Until the next time, stay away from trouble. Keep learning, keep living, and keep bettering yourself. Okay? Bye.